Brandon, here with the second last chapter. We are wrapping things up by looking at the highest level of automation maturity. When you work in government or critical infrastructure, the rules are different. It is not just about making the network work. It is about proving that every single action followed the law. Archird is going to explain why an unprovable system is a failed system, and how to build for the strictest regulations in the world. Let us finish strong.
Chapter 10: Security, SOCI, and Government Constraints. Automation does not seek to bypass regulation. It seeks to make compliance a programmable outcome. In a regulated environment, an unauthorized script is a security incident waiting to happen. The unprovable system problem. I've reviewed automation systems at critical infrastructure sites that were technically sophisticated but operationally illegal. They could set up networks faster than any manual process, but they couldn't prove who approved the change, couldn't demonstrate separation of duties, and couldn't show that unauthorized access was prevented rather than merely discouraged. The first time a regulator reviewed these systems, they were shut down. Not because they were unsafe, but because they were unprovable. In regulated environments, a capability you cannot prove is a capability you do not possess. This chapter addresses the hardest constraint in enterprise automation: satisfying strict regulatory requirements whilst maintaining the speed of code-driven infrastructure. If you finish this chapter believing that compliance is something you add later, or that security is separate from architecture, you'll build systems that fail their first regulatory review. The regulatory reality. For organizations operating critical infrastructure, power grids, telecommunications networks, financial systems, government services, the operational bar isn't merely high, it's absolute. The Security of Critical Infrastructure Act, along with various government cybersecurity frameworks, demands more than just good security. It demands verifiable resilience. In these environments, your architecture must address three specific challenges. The insider threat constraint. The system must technically prevent a single person from making a significant change alone. This is often called two-person integrity. Your code repository and your deployment pipeline must be configured so that one person writes the code and a different authorized person approves it before the system can execute. The sovereignty constraint. You must know exactly where your data and your management systems live. In many government contexts, using a public cloud service to manage a private power grid is a violation of national security policy. Your architecture must be able to run air-gapped or within strictly controlled local environments. The immutable audit constraint. It is not enough to have logs. Those logs must be stored in a way that they cannot be altered, even by the person who has God mode access to the network. This proves to regulators that the history of the network hasn't been tampered with to hide a mistake or a breach. Compliance as code. The secret to succeeding in these environments is to stop treating compliance as a manual paperwork exercise. Instead, you turn the regulations into automated tests. If the law says all changes must be approved by a level 4 manager, your Python code checks the digital signature of the approver against the company's HR database before it allows the change to proceed. If the signature doesn't match, the change is blocked. You haven't just followed the law, you've made it impossible to break it. Takeaway. In critical infrastructure, the goal isn't just to automate the network, it's to automate the evidence of compliance. The core principles of this book. These principles form the foundation of enterprise network automation. They're not negotiable in regulated, high-stakes environments. Architecture trumps tooling. Select the layers and connections first. Select execution engines second. Tools implement architecture. They don't define it. Version control is the source of intent. If it's not in the repository, it didn't happen. The repository is the authoritative record of what the network should be. Control layer is the enforcement boundary. Use Python to validate, gate, and coordinate every change. The control layer prevents invalid changes from reaching production. Governance is a feature, not a constraint. Auditability is the product of automation. Build traceability, approval verification, and rollback capability into the architecture from the beginning. Safety is the metric. Success is measured by safe-to-fail reliability, not by speed or automation coverage. Trust is built through graceful failure, not perfect execution. If you finish this book believing that automation is primarily a technical challenge, you've missed the fundamental lesson. Automation in critical infrastructure is an organizational capability that must be designed for longevity, governance, and resilience. Build platforms that will outlive their creators. Design architectures that will survive tool migrations. Create capabilities that regulators can audit with confidence. This is enterprise automation.
We have reached the end of the second last chapter, through network automation architecture. I hope these chapters have given you a new perspective on how to build systems that are not just fast, but safe, governed, and truly professional. Remember, the goal is to build something that outlives any single tool or person. If you enjoyed this series, please make sure to subscribe and share it with your colleagues. Thank you for listening, and I will see you in the final chapter.